Hey everybody. So this is lesson 4D, graphing vertex form, chapter 4.4. So last week we talked about the standard form. Yeah, so let me just rewrite that back out. So the standard form was y equals a x squared plus bx plus c. We also talked about the fact that each one of these forms, whether it be the standard form, the vertex form, which is what we're going to talk about today, and the factored form, which is what we're going to talk about next lesson, each one of those forms gives us a different characteristic of the parabola. So from the standard form, our c value, or our value at the end, tells us our y-intercept. Okay? The vertex form, as the name implies, tells us our vertex, which, once again, is either the minimum point, the lowest point, or the highest point of our parabola. Okay? So, here is the vertex form. What do each of these variables mean? Well, let me just move this back up for a second. Last week, we also talked about, or last lesson I should say, our a value told us whether our graph was vertically stretched or compressed. Okay, these a values are the same thing. Okay, this a value will tell us whether our graph is vertically stretched or compressed. Okay, and think back to transformations, which was last lesson. H shifts our graph left and right, and K shifts our graph up and down. Now, when I say that these a values are the same, I mean, technical difficulties. I mean, if I were to switch over to Desmos and I were to write y equals 2, so x squared, don't worry about this right now, I'm just doing some quick maths, plus 5 and plus 18, 18 plus 5 plus 23 minus 12x. Okay, so if I look at these two graphs, this one graph, I'll see that they are the same parabola written in two different forms. You've got the vertex form and the standard form. Now, what we said last week, or last lesson I should say, or 2 lessons ago, was that this is our y-intercept, and it sure is. Now, we also talked about transformations, and that's what this 2 value told us. It told us our vertical stretch or compression. In this case, it's a vertical stretch of 2. Now, if you notice, this a value is the same a value as the one in the standard form. Okay, they're both being vertically stretched. Okay. Does this negative 12 or our b tell us anything? Not directly, no. Okay, so let's go back. Now, if I take a look at the vertex form, if this shifts our graph left and right, and this shifts our graph up and down, then wouldn't it make sense that, let's say, let's pretend this is touching the origin, okay? If I were to take this parabola and shift it to the right by h, so let's call this h, and then shift it up by k, up by k, then wouldn't this point be h and k? Sorry. Which means the new vertex would be right there. Okay? So if I go back to Desmos, you will see I'm shifting my graph over, my parabola, to the right by 3, and then shifting it up by 5. Well, what does that tell me then? Then that tells me that my vertex is at 3 and 5. 3 and 5. Okay? So, let me just be more explicit about that. Okay, so that means h and k is our vertex. Okay? and this is still our vertical stretch or compression. Okay, now let's put this in action. Graphing with vertex form. Oh, a couple terms here, sorry. Let me just scroll back up. So our axis of symmetry. We've already talked about this. This is where our graph cuts it perfectly in half. Or our parabola. So let's say our parabola is right here. Okay. I'm going to draw little arrows. And let's say this is our axis of symmetry. Let's call this number 3. So let's say the vertex, I'm going to make it up. Let's say the vertex is 3, 1. Yeah, so that in this case would be the minimum point. Now, if that vertex was 3, 1, then wouldn't that imply that our axis of symmetry, or where our graph is completely cut in half, would also be at x equals to 3? Okay, which means our axis of symmetry is usually at x equals to h. So in other words, whatever our x value is of our vertex. Okay. Now if I switch over to decimals for a quick second. Okay, so if I just change, so let me just delete these, and I'm going to write any vertex form. So x minus 4 plus 6, let's say. Oops, I forgot the square up top. Then that means I know our vertex is at 4, 6, which means our axis of symmetry should be at x equals to 4. And sure enough, I'm just going to make this dotted so it's clear. So sure enough, our x equals to 4 is indeed our axis of symmetry. And there you have it. Okay. Now stretch and compress, you already know. Vertex is at hk, and direction of opening, this implies it's opening up. This means it's opening down. Sad face is opening down, happy face is opening up. Okay. Scroll down a little bit. Okay, so domain and range. You know what, I could talk about it briefly. Yeah, let's quickly talk about it. With domain, this just strictly means all of the possible x values. Okay? Whereas the range is all of the possible y values. Okay? Now what does that mean? Well, if I were to draw a quick little sketch on the side here, okay, and again I'm going to choose a vertex of, I don't know, I'm going to make something up. Let's say 3, 1 again. So if I were to ask you, what are all the possible x values? In other words, are there any other x values that are not possible? So if I look at this, all the x values would go anywhere on the x-axis, because these arrows imply this goes on forever and ever and ever, right? So what are the all possible x values? All of them. All. So if I put D for domain, all x values are possible. Okay. Now, if I were to look at y values, are all y values possible? Or I'm going to put R for range, sorry. No, because the y values must be bigger than 1. Because the graph starts at 1, if we strictly look at the y-axis, starts at 1 and heads up. Okay? So all y values bigger than or equal to 1. Okay? There is a proper mathematical notation in writing out domain and range, but we'll talk about that at a later date. Okay, now graphing with vertex form. It's actually pretty straightforward. So y equals 2x minus 1 squared plus 5. So the vertex I know is at 1, 5. So remember, the sign switches. Negative 1, it should be positive 1. So the vertex would be at 1, 5. I'm going to make this a little smaller. And scroll, whoops. Make this a tiny bit smaller. Okay. So my vertex, I know, would be at 1, 5, which is right there. Now, then I ask myself, is this going to be opening up or down? In other words, is it going to be a happy face or a sad face? Well, how do we find out? So here's 1, 5. I don't know why it disappeared. Okay. Now, if I look at this equation again, if my a value, so again thinking back to transformations, is bigger than 1, then I know it would be opening up. Okay? Because a negative a value implies there's a reflection, which means it will be opening down. So because a is positive, so a is bigger than 0, then it's opening up. So I know my graph is going, or my parabola is going to look something like that. Now, however, I know that it's going to be vertically stretched by 2. But I want to determine how to sketch that if it's vertically stretched by 2. Well, to do that, what I'm going to do is take a look at the parent graph. So let's go to decimals for a quick second. And if I were to sketch the parent graph, so y equals x squared, I want you to take a look at something. So if you look at the parent graph, there should be a pattern for all of these parabolas. And that is, if I were to start at the vertex, okay, I will always be going over 1, and then how long does it take for me to hit the parabola? Up 1. And if I go over 1 again, I go up 3. 1, 2, 3. I wonder if this pattern stays true for all parabolas that are not stretched or compressed. Let's keep going. 1 over, and then up 1, 2, 3, 4, 5. Let's see. So if I were to draw a table of values, so let me just include a table, and then if I were to write, let me just delete that, delete. I'm just going to change this to y1, okay. So if I were to write, let's say 1, 3, 5, oh sorry, 5, or not 1, 3, 5, sorry, 1, 2, 3, okay. Here is our graph. Well, does that make sense? 1 squared is 1, 2 squared is 4, 3 squared is 9. Here are our 3 points. If I go 1 over, 1 up, 1 over, 3 up, 1 over, 5 up. Now, because it's symmetric, I don't need to check the other side, but let's check it anyway to be safe. 1 over, up 1, 1 over, up 3, up 1 over, up 1, 2, 3, 1 over, up 1, 2, 3, 4, 5. Okay, so it is symmetric. We can assume that it's going to be the same on both sides. Now the point I'm getting at here is, I wonder if this pattern will always stay the same. Because if it will, that will make graphing the vertex forms very, very easy. So let's take a look. I'm just going to change the vertex to whatever I want. Let's go -1 plus 3, let's say, which means our vertex is at 1, 3. 1, 3. Now let's see if my pattern still holds true. So, at 1, 3. So if I go over 1, up 1? Yes. Over 1, up 3? 1, 2, 3. Yes. Let's see if I go over 1, up 4. I'm just going to add a 4 down here. Okay. So 1 over up 1, 1 over up 3, 1 over up 1, 2, 3, 4, 5. This is what we call the 1, 3, 5 pattern. Okay? The 1, 3, 5 pattern. Which means that as long as the vertical stretch is at 1, that pattern will always hold true. So I'll just use a different, let's switch a different vertex just to prove a point. Or even, okay. So let's see, what's my vertex? Negative 1, negative 2. Negative 1, negative 2. Let's see, the 1, 3, 5 pattern still holds because my A value is 1. Over 1, up 1. Yep. Over 1, up 1, 2, 3. Yep. Over 1, up 1, 2, 3, 4, 5. 1, 3, 5 pattern. Holds true. Okay. Now, my question then is, what happens if the A value is not 1? Well, remember, the A value, or in other words, the vertical stretch or compression, will only affect the Y value because we're vertically stretching or compressing it. We're not horizontally stretching or compressing it. We're vertically stretching or compressing it. So let's change it to 2. Let's see what happens. If I go 1 up, I'm not going 1 up anymore. I'm going 2 up. If I go 1 over, am I going up 3? No, but instead I'm going up 1, 2, 3, 4, 5, 6. So remember, let me just switch over to our worksheet for a second. So I know right now that for the parent graph, I'm going to put P for parent. It's typically 1, 3, 5. But for our current one, okay, our current steps, what are they? They're not 1, 3, 5, but instead they are, in fact, let me type in this exact one on Desmos. 2x minus 1 plus 5. Okay, so which means this is what, once I sketch this, it should look something like this. So the vertex is 1, 5. We already know that. It's 1, 5. And then instead of going 1 over 1 up, we're going 2 up. So instead of 1, it's 2. And then 1 over, and then up 1, 2, 3, 4, 5, 6. So instead of 3, or instead of 1 over 3 up, it's 1 over 6 up. So now the next one, if I were to zoom down a little bit, let's move this down. If I go 1 over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up, I'm going 10 up. Okay. So, what do we notice? Well, the pattern, everything just got doubled. And why did it get doubled? Because everything was vertically stretched by 2, which means we just take the parent function and multiply the 1, 3 step pattern by 2. And that's it. Okay, so now how do we use this to graph? Well, it's as simple as finding the vertex, which we already said was 1, 5. Okay, then we go 1 over. So 1 over, and then we just check my scale. Okay, so 1 over, and then I go over 1, and then instead of up 1, I'm going up 2. So 1, 2, that would be my next point right there. Okay, now, here, I can go 1 over, and then instead of up 3, I'm going up 6. Okay, so I'm going to go up 6. So I'm at 7 now. 7 plus 6 is 13, so it'll be right there. Okay, and then I can go over 1, and then up 10. Okay, so if I am at 13, that's going to take me to off the page. Okay, so once again, oh, I don't know where this one went. So it was supposed to be up over 1 and then up 6. Or sorry, up 2. Over 1, up 2. So it's supposed to be right there. Okay. Now, the last one was 1 over up 10, which will go off the page. Now I'm going to do the same thing on the other side just so I have more guiding points. Over 1, up 2. Oh, whoops, I made a mistake on the other side. It's supposed to be over here. Okay. And then over 1, and then up 6, which would be about right there, 13. Okay, and now from here, I can just simply sketch this and connect the dots. Okay, so this should go off the page. Whoa, this is going to be bad. Let me just try retracing this. I need to calibrate this, I think. So this is probably the worst parabola I've ever drawn in my entire life. Okay, so let me show you just one more example, and then you should be able to do the rest on your own. Okay, so the vertex here, vertex would be at 1, -4. Okay, so the vertex at 1, -4, I'm going to label each of these, let's say, so picking your scale is key. So if I go 1 over, down 4, okay, so what I'm going to do then is label all these. Your x-axis and y-axis do not have to be the same. Okay, so 2, and then 0, and then label this one -1, -2. And then down here, I'm going to label each of these as -2, -4, 2, 4. Okay, so the vertex of 1, -4, 1, -4 is going to be right there. Okay, so now I know what the vertex is. I can use the 1, 3, 5. So 1, 3, 5. But instead of 1, 3, 5, I need to multiply everything by 2 times 2. So that would give me 2. So 3 times 2 is 6. 5 times 2 is 10. So that means I'm going to go 1 over. It's always 1 over. So 1 over and then up 2. 1 over up 6. And then 1 over and up 10. But obviously that's going to go off my page. Do the same thing on the other side. 1 over up 2. And then 1 over up 6. And there you have it. Now all you got to do now is connect the dots. And you want to try to keep a smooth curve. This is a lot harder to do on the screen. Let's pretend that hit that point, okay? And there you have it. So for this one, it'd be the exact same thing. Start the vertex -2, -2. But instead of 1, 3, 5, you'll be multiplying everything by 3. So then this becomes 3 times 1 times 3 is 3, 3 times 3 is 9, 5 times 3 is 15. So you go 1 over from the vertex, up 3, 1 over, up 9, 1 over, up 15. Okay, thank you. Any questions? Post on Google Classroom. Okay, bye.